Okay, I just told you the statement and now I'm going to break this rule. Okay, so let's talk about ions versus atoms. So atoms can change. Obviously, they aren't static. Atoms are not static. And they change. They can take on different forms. One of those forms is an ion. The difference between an ion and an atom is that an ion has a charge, an overall charge. So ion has an overall charge. Okay. So the process of ionizing or ionization, you might hear me call it by either, is the loss or gain of electrons by an atom. So it might lose electrons in order to get a charge, or it might gain electrons in order to get a charge. So here's an example of that. So hydrogen, oftentimes we see it as a hydrogen ion, as H+. Chlorine, oftentimes we see it as a hydrogen ion, and it's a Cl-. Now we give different names to these different charges. So if it has a positive charge, we call it a cation. I like to think of cation, it's got the plus sign in it. And for negative, we call these an anion. So just different types of ions, and it tells you if it has a positive or negative charge. So sometimes you might see more than just a single positive or single negative. You might see like a +2 or a +3 or a -2, -3, all right? It's not just the standard one. And what you need to remember is that atoms are like magnets sometimes, and they pull these charges to and from, okay? So let's see an example of why this is useful. So lithium ion batteries, if you've ever heard of these are important pieces of technology, and we use these in all kinds of applications. We use them in cars, we even use them in like standard batteries. We have them now, like Duracell batteries, you have lithium ion batteries. So let's take a look at how these use lithium ions, so Li+. So here's an example of the charge. Charges are electrons, so whenever you're charging your car, so when you're driving your car here, you can see you're in driving mode, you can see that the lithium ions move to one side of the battery. Remember, batteries have terminals, positive and negative charges. And when you hook up your car to be charged, the electrons go the other way, to the other ends, and the lithium ions move, okay? So this is, you're seeing these charges attract. Lithium ions are positive, and the yellow little dots you see moving are negative electrons. Negative attracts positive, which is why it's moving from one side to the other. So let me write that down so you can kind of see that a little better. So lithium, positive, gets attracted to electrons because they're negatively charged. The electrons here, these were the electrons moving, and these are your lithium positive. So when you see the electrons go to one side, the lithium atoms follow. And that's how charging a battery works with ions. Okay, so now I want you to take a second and think about this. There's going to be a quiz that pops up. And think about what might cause an ion to exist. What changes might happen to an atom as far as subatomic particle amounts in order to form a charge on a hydrogen atom, a cation like H+, versus an anion like Cl-. What subatomic particles might be changed here? Would you see an increase or decrease in protons, neutrons, or electrons? So what you should have seen here is that in order to get a positive charge on hydrogen like that, what we're going to need to do is we're going to need to have more protons than electrons. Whenever you have an element on the periodic table, like hydrogen, we say it has 0 charge. What that means is that your protons are equal to your electrons. Now, all of a sudden, if it gets a positive charge, that means we've got more protons than we do electrons. So what's happening here is we lose a proton, or we lose an electron. So we lose one of these, and all of a sudden, now we've got more protons, and so we get an H+. The opposite happens for chlorine. So chlorine from the periodic table has no charge. Protons are equal to electrons. But in order to get that negative charge, we need to have an imbalance between them. So what we can do is our electrons goes up. And when that happens, we gain an electron. And so we end up with a negative charge. Another interesting trend on the periodic table is that these ion charges that atoms tend to adapt are based on where they're located on the periodic table. So we saw our hydrogen form a +1. We saw our chlorine here form a -1. Every other element in that column with those elements forms the same charge. So lithium forms a +1. We saw that as an example. It's in that same column. This beryllium here, Be, and magnesium will form a +2. So they'll be like this, Mg2+. You'll see that one a lot. Fluorine will have a -1. Oxygen, when it becomes an ion, it tends to form O2-, a -2 charge. These right here, you'll notice, are a 0. We're going to discuss why. I'm going to tell you why all this happens. I don't like leaving you all in the dark. They don't like to lose or gain electrons. They're quite stable. So why does this happen? Why do we have specific numbers of electrons gained or lost depending on where an atom is on the periodic table? So why this happens is because our valence electrons, remember these are our exterior electrons, and these are electrons that give our atoms their chemical capabilities because they're able to bond with other atoms and they're in the outermost shell. So these are our valence. These want to form an octet, right? So all electrons like to form an octet. Our valence electrons want to form an octet. An octet is 8 electrons, and it's a very stable electron formation. It consists of 8 electrons inside of an electron shell. So you'll see in that outer shell, there's 8 there. In this inner one as well, there's 8 here. This guy's a little bit special. There's only 2 here, so we're going to ignore that for now. It doesn't form an octet. It's an exception to that rule, but all the other electron shells, the second and the third and the fourth and fifth and sixth, all want to have 8 electrons inside of them. Okay. So if we count on chlorine, we've got 1, 2, 3, 4, 5, 6, 7 electrons. There's 1 missing. If we look at what's called a Lewis structure over here, Lewis structures only show valence electrons. We can see that there's 7 electrons very clearly around our chlorine. So what this means is that an atom can achieve an octet if it ionizes by gaining or losing an electron. So it does, because it's more stable that way. So what happens is our chlorine gets an electron. It comes right in there. It fills these holes, okay? So if we look at what the atom actually looks like, you'll see there's an electron that's been added to the outer shell. And now it's got 1, 2, 3, 4, 5, 6, 7, 8. It's very happy. Okay, so here, to emphasize this, I'm gonna draw like a sad face, okay? Happy, it's this guy's sad. And then we make it happy. All right, oh good. So it's more favorable for it to ionize. So if we look at the Lewis structure here, you see now it's got 8 electrons in its shell. It's got a negative charge up here because it gained an electron. Okay. Something that you'll notice that you saw on the periodic table is that some of our atoms don't ionize. Okay. So one of these was neon. Let's go back to here. We're going to take a look at neon. Neon's right here in the periodic table. It's in group 8. It does not ionize. So when you look at neon, what you're going to see, you're going to see 2 electrons in this inner shell. And then you're going to go to the next shell. Remember, it's in period 2. It's got 2 electron shells. So the next shell, and it's going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that shell. 1, 2, 3, 4, 5, 6, 7, 8. Great. It's got a total of 10 electrons. You can see the 2 on the inside. That's why it's got that 10 there. That's the number of protons inside. So we've got 10 protons in here. 4, 5, 6, 7, 8, 9, 10 in there. All right. And if we look, well, you'll find that our neon's quite happy because it's got 1, 2, 3, 4, 5, 6, 7, 8. It doesn't want any more. It doesn't want to gain electrons. It doesn't want to lose electrons. It's fine. So it tends to not react. It will stay as is. An example of a cation losing electrons, let's look at our lithium. So lithium over here, it's in our second period. So it's got 2 shells, 2 electron shells, 1, 2. This right here, because it's in this row, it's going to tell us there's 1 electron in its valence shell out here. Okay. And so what happens is if that's a bad example. Hold on. Let me undo that. Okay, let me choose a different example. Lithium, that's going to be an exception to the rule. Let's look at sodium. Okay, sodium. Let's go down here. It's in group 3. 1, 2, 3. It has 1 electron in its valence shell because it's in that group 1. Inside of its previous shell, it's got 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that comes from here. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons there. And inside our inner shell, there's 1, 2. So if you wanted, you could put the 1, 2 there. Okay, so each of these rows kind of tells you how many electrons are in each electron shell. And then the total number is indicated here. So if you counted up all the electrons, you find there's 11 total. Now, what happens in sodium is sodium wants to have an octet because that's more stable. So it takes this guy and it kicks it out. It leaves. When it does so, now the next shell on the inside becomes its valence shell. And so now it's got 1, 2, 3, 4, 5, 6, 7, 8. So now it achieves an octet by letting an electron leave, which is why it forms a positive charge most of the time. So all these other atoms follow similar processes, which is why they form the charges that they do. Okay, so now you're going to have a practice question to kind of put all this together. So see if you can figure out how many particles, subatomic particles, each of these atoms and ions have. So you want to fill out this table. So you'll see an answer that says what goes in B1, that goes here, or what goes in B2, that's going to go here, okay? So you want to look at the number of protons for each of these, the number of electrons, number of neutrons, number of electron shells, number of valence electrons. And then the atomic masses, you can look up from the periodic table. So straight from there, you can do that. Okay. Make sure you use your periodic table to do this. If you're using atom.phys, that's not going to be allowed on exams. So you need to be able to look at the periodic table and figure that out, okay? So don't cheat on this one. You can use atom.phys to check your answers, but attempt it with the periodic table first and give it your best shot. Okay, so what you should see here on this problem is that magnesium, when we go to our periodic table, I gotta go find it. Magnesium here, 12 and 24. Okay, so magnesium here is 12 and 24. I think it was 24.31. So that's our atomic mass, 24.31. The number of protons here is indicated by this. So it's got 12. Because it's magnesium, we'll go to the ion next, sorry. Okay, so this also indicates the number of electrons if it's not an ion, so it's also 12. Number of neutrons. Number of neutrons comes from our mass. Remember that our mass is protons plus neutrons. So we need to find out how many that is. So we're going to round to the nearest whole number. So that might have tripped you up this time. We're going to talk about it in just a second. So we're going to round to 24. Because that's protons plus neutrons, we know how many protons there are is equal to 12 plus x. These are neutrons. So to solve for x, subtract 12. And we find that x equals 12. So we have 12 neutrons here as well. Number of electron shells. If you look at your periodic table, magnesium is in the second row. So 1, 2. It's got 2 electron shells. Number of valence electrons. This is going to be the same number because you actually go over. It's in the second row. So it's in 1, 2. So the second group, which gives you 2 valence electrons. All right. Now let's take a look at the ion of magnesium. Because it's still magnesium, the identity has not changed. That means that it's still in the same location on the periodic table. If you change this number here, you change the identity of the ion, of the element. So if you change this to say 11, then if we look back at our periodic table, you'll see that's a whole new atom. That's sodium now. You cannot change that number at the top, the atomic number, without changing the identity of the atom. So make sure you're careful there with changing that. So this is also 12. It's not going to change there. Number of electrons. Number of electrons does change because we see this charge here. Remember, the definition of an ion is that it gains or loses electrons. In this case, there's more protons than there are electrons. So we've lost 2 electrons. So now we're at 10. Number of neutrons, also the same because our mass has not changed. Our mass number is still 24.31. Number of electron shells. Okay, so this has changed. So has our valence electrons. So remember, magnesium was here. It's in row 2. It had 2 on the outside. It lost those. Those went away. And so we're going to be left, I believe, let's see if I can find, this periodic table isn't in the right location. I was hoping. Okay, we'll go back a little more. I apologize. Oh, sorry, it's in the third row. I made a mistake. Okay, it's in the third row, which means that it has 3 electron shells. Sorry. Okay, valence electrons are the same. So it has 8 in here. Boop, 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 boop. 8. So if you lose 2 electrons to get your positive charge, that means now you're down. This electron shell is gone. So now we're down to 2 electron shells. Number of valence electrons is now 8 because we've lost our outer shell. It's stable. It's achieved an octet by losing those 2 electrons. The atomic mass is still the same number because ions only involve electrons, and we know that electrons have no mass. And therefore, changing the electrons cannot change mass. So let me know if you have any questions on this.